So we can go straight then to the first talk of the first session of this NCTS Annual Theory Meeting. So our first speaker today is Francesco Buscemi. I've known him for many years. I don't know how many years, maybe more than 10 by now. So he's, I think he must have been promoted to become a full professor at the Department of Mathematical Informatics at the Graduate School of Informatics at Nagoya Universities. So he is an expert in quantum information theory. I mean, he had his PhD, I think, from the University of Pavia, if I
Yes.
mistaken. So he's an expert in quantum information theory, quantum thermodynamics, quantum statistical mechanics, measurement theory, quantum foundations. And he was also the recipient for this Birkhoff von Neumann Prize back in 2018. So I guess he's more than qualified to tell us something about second laws of thermodynamics and so on. So the stage is yours, Francesco.
Okay, thank you very much. Those are my research interests. I'm not claiming to be an expert in each of those, but anyway.
I'm sure that you are.
So thank you very much for the introduction, and thank you for inviting me to give a talk. So I will begin this talk with an introduction, which is itself a result. It's a published result that I had with my students, but which for us today will mostly serve as a pretext for the main point, that is the role of retrodiction in statistical mechanics, and in particular in thermodynamics. So the starting point of our considerations is a kind of very vanilla scenario for an open quantum system evolution, where you have a system interacting with some ancilla. I call it ancilla because it could be a thermal bath, it could be a work reservoir, that is to say a battery, or it could be a memory. Anything else, so you have like anything else that interacts with your system. And the interaction is driven by this total Hamiltonian. So as a whole, the thing goes as a Hamiltonian evolution, and you have some Hamiltonian, in particular this interaction term, they all depend on time in general. So you have some driving protocol there. And we know that if the system and the ancilla start in a factorized form, so this is like the vanilla scenario for open quantum system evolution, the state, the reduced state of the system after the interaction, so when we reach final time t equal tau, is given by this formula where you have this partial trace over the ancillary degrees of freedom. And we know that this can be represented as a CPTP map, a completely positive trace-preserving linear map that transforms the initial state of the system into the final state, rho tau. So if this interaction region is sufficiently small, then so we can imagine that the initial time and the final time are essentially like boundary conditions for this scenario. It is quite relevant in thermodynamics to consider the system's average energy change. Why? Because, well, this is a crucial quantity for thermodynamics, because depending on the situation, this can measure the work that was put into the system by the driving protocol. It can be considered to be the heat exchange with the bath, in case you have a bath, and in case the system energy change can be seen as a heat. It can be seen as the irreversible entropy produced by the driving protocol, and so on. So a central quantity in open quantum system dynamics is this energy change of the system. So then we can try to evaluate this energy change. And a typical calculation is this one, where D is the usual quantum relative entropy, so an information divergence, and delta S is the change of entropy in the system. So here I assuming, just for simplicity, that the system starts in thermal equilibrium. If not, you have to add more terms, but basically the point is this. So in particular, if you consider the evolution of an closed driven system, so even if the Hamiltonian is dependent on time, you have Dyson expansion, so you know that the total evolution is still unitary. So unitary evolution tells you that delta S is 0. So it means that for a closed driven system, this information divergence between the final state and the final equilibrium state, right, quantifies the energy change. So intuitively speaking, right, this tells you that the further the system is drawn away from equilibrium, the more irreversible the process is. So this is something that is well known. It is a very simple calculation. The point is that because of, in general, so when the process is not closed, but it is open, when there is actual interaction with an ancilla, in general, this delta S is not zero, but can be positive or negative. Therefore, in general, there is no direct connection between this information divergence and the energy change of the system. However, there is also another way to evaluate the energy change, and that is given by the following formula. Again, don't look so much at the terms themselves, but well, these are just obtained by adding and subtracting terms as it is suitable. So you see that the energy change can always be written as an information divergence, which is different from this, okay? We will come back on this point, plus the average of this self-adjoint operator. So phi daga here is the trace dual, or the Heisenberg version of the CP-TP map phi. So now a very important thing is that this self-adjoint operator here was proved by Choi in 1974 to be always positive semi-definite. So in the case of an open quantum system dynamic, while this lower bound does not hold in general, this bound always holds. So you can say that essentially, if you want to understand, to evaluate the energy change of your system, then rather than looking at this distance here, this divergence here at the final time, you'd better look instead at this divergence at initial time between the initial state, the state where you started from, and this kind of pullback thermal state at final time, pull back via phi daga to the initial time t0. So this is a curious object, this phi daga gamma tau, right? It's a curious object that indeed this line of research that I'm going to tell you about started in the attempt to understand the role of this object. So what is it? We can call it like the thermal pullback. Why? Because it takes the final state of thermal equilibrium and brings it back to the initial condition. You can normalize it in this way, so the trace comes up here. Now, this thing is always positive, right? Because it's a relative entropy between two normalized states. And therefore, you can say that it is greater or equal than this lower bound here. And there are various connections here. So this number here, the trace of phi daga gamma tau, already appeared before in some previous papers, and it is called the efficacy. And when this thing appears, typically you are working with fluctuation relations. These are two papers that consider this term in relation with fluctuation relations in particular. And another curious thing about this pullback, thermal pullback, is that the pullback mapping is completely positive trace preserving by definition, but it is in general non-linear. Why? Because here we are normalizing by the trace of the input. So this correspondence here in general is non-linear. So here is the paper that I wrote with my students about this bound. But now we want to take these ideas as the starting point for the next part, because I would like to tell you if this pullback mapping reminds you of anything, this kind of non-linear updating. Well, just by using the word update, I already put you on the right track, because it is reminiscent somehow of the Bayes-Laplace rule, at least to me. Bayes-Laplace Rule, also called the formula of inverse probability, is a rule that is there in all basic textbook of probability theory that tells you how to update a prior distribution on a set of mutually exclusive hypotheses, PH, to a posterior distribution in the face of some data, D. Okay, here I don't want to, don't want to get into any kind of interpretation of prior probability, posterior probability. We are going to use Bayes-Laplace rule as a tool. Fortunately, we live in a postmodern world where we can use ideas without subscribing to any particular ideology. So I will be very postmodern today. I will use Bayes-Laplace rule as a tool to work and see where we can go using Bayes-Laplace. So what is the inverse probability? Just to give you a quick refreshment on inverse probability. So inverse probability is the main tool of Bayesian statistics for problems like estimation, decision, predictive inference, like predicting the weather tomorrow, but also retrodictive inference. And there are sciences that are only retrodictive in nature. Think about astronomy, for example. There we cannot prepare cosmological objects and make them collide, for example. We can only look passively at the sky and receive data and retrodict, for example, the kind of stellar events that caused those observations, right? But also inverse probability can be seen as the degree of belief that a rational agent should have about one hypothesis given the data. So it's a very important tool for reasoning logically about data and see how belief back propagates or propagates in a Bayesian network. But one thing that it is not often highlighted is the following, that Bayes-Laplace rule does not tell us how to update the prior in the face of uncertain data. So in the formula of Bayes-Laplace rule, here D is considered to be a well-definite value of the data. But typically data are not given to us as well-definite. You can always imagine that there is a margin of error even in reading the data itself. For example, suppose that for my inference, I need to know the license plate number of a car. So I will use the license plate number of a car to update my prior about something else. But imagine that the data is given to me as a very noisy picture like this one. So here I cannot really give a well-definite number to this license plate. I can basically try to guess. So I can imagine that this picture here would give me uncertain data. And for example, I can imagine that these uncertain data are given to me in the form of a probability distribution on the data, some Q. So how should we update our prior given uncertain evidence in the form of a probability distribution on the data? Bayes-Laplace rule does not tell you anything about this scenario. In order to deal with this scenario, we need something more. And this something more is so-called Jeffrey's rule of probability kinematics. So this is the vanilla Bayes that gives you the posterior for a certain value of D, data D. But what about the generalized Bayes, where the data is given as a probability distribution, not as a delta on the data? And the rule is given by Jeffrey, so-called Jeffrey conditioning, that was proposed in 1965 by Richard Jeffrey, which was a famous philosopher of science, logician, and statistician. Not to be confused with Sir Harold Jeffreys, which is also a famous Bayesian statistician of the 20th century. So basically, Jeffrey conditioning rule tells you that given uncertain data as a probability distribution, you should use the inverse probability that Bayes' theorem tells you, not as a number, but as a channel, as a noisy channel that propagates. You see that here I am summing over D, propagates your uncertain information D from the data onto the hypothesis H. And here, just by expanding, by using normal Bayes rule. So we have seen, until now, we have seen reverse bounds, we have seen pullback mapping, inverse probability, retrodiction. And in the formulation of the second law too, there are many retro things, right? For example, the second law itself is always understood to be, often understood to be about reversibility or irreversibility of the process, right? But in particular, what I have in mind here is the formulation of the second law in terms of fluctuation relations, and in particular, reverse processes. So I would like to have just one slide about reverse processes in thermodynamics. One can imagine that when you consider a macroscopic system, you don't have really fluctuations, right? If you repeat some predetermined thermodynamic protocol, you will always read the same amount of work, for example, or the same amount of entropy or the same amount of heat. But when the system becomes small, then statistical fluctuations matter. And indeed, you can imagine a situation like the following one, where you have a piston in thermal equilibrium with some thermostatic environment around. And then you plunge the piston inside up to a certain level. And this will be your forward process. And you can repeat this many times. And if the number of molecules basically inside the piston is small, every time you repeat this forward protocol, you will read a different amount of work that is needed to you to push the piston in. But you can also consider the reverse protocol, where you start with a piston in compressed position. Again, you are in thermal equilibrium, and now instead you pull the piston out to the exact initial condition of the forward process. Also here you will read different values of the work that you were able to extract from the molecule for the few molecule gas inside the piston. And you can actually construct the whole work distribution for the forward process and the reverse process. Now, it is a highly surprising fact, in a way. The first time you see it should be extremely remarkable to you to know, to learn that this work distribution of the forward and the reverse process are not completely independent, but satisfy this fluctuation theorem. So how can we give an interpretation to this? So for example, like in the forward process, you can do some work W. So the probability to perform work W in the forward process divided by the probability of extracting work W in the reverse process is given by the exponential. And here we have to keep in mind that beta for like everyday situations is an astronomically huge number. It's basically of the order of the Avogadro number, 10 to the 22, 10 to the 23. And so this means that for macroscopic situations, for everyday situations, there is an extreme asymmetry between the work distribution in the forward process and the work distribution in the reverse process. But nonetheless, however these things are, they will cross exactly in one point, and this point being the difference of free energy. So in this point, you're doing your process in a quasi-static way, right? The work that you do is exactly equal to the difference of free energy. So in that point, the two things will cross. And this fluctuation theorem, beside giving you this nice insight about what happens in a in a small scale thermodynamic process, it also entails Jarzynski equality, which is a considerable strengthening of Clausius equality that dates back to 1865. So after 140 years, basically, by moving terms around in Clausius inequality, people were able to derive an equality, and even more to give a kind of intuition why this equality works, right? Because Crookes fluctuation theorem is more general. It implies Jarzynski equality. So then one could ask, so why Crookes fluctuation theorem works, okay? What's behind this? And the idea is that there is no new physics. It's everything basically boils down to equilibrium thermodynamics, because the assumptions are basically that the initial distribution is a thermal distribution. And then the other assumption is the validity of microscopic reversibility, which is a concept that is not clearly explained in the literature. There are papers written about the meaning of microscopic reversibility, but loosely speaking, this is defined, for example, on Wikipedia, it is defined as the property such that at equilibrium, molecular processes and their reverses occur at the same rate, that is to say, with the same probability. So then one would say, wait a second, so do fluctuation relations and therefore the second law rely on some kind of microscopic balancing mechanisms that happen at equilibrium, right? Because it seems that these molecular processes balance them. Well, I would not be so keen about this interpretation, right? Because that would mean that essentially these fluctuation theorems hold because of some property of the Hamiltonians there. Indeed, when people construct reverse processes, typically they start from the Hamiltonian and then they flip terms in the Hamiltonian, consider, for example, whether there is a magnetic field or not, whether it is you're flipping a variable that is symmetric in time or not, like a momentum or a position. So people really work at the level of Hamiltonian. But here I would like instead to try to follow Jaynes, that in his paper, Predictive Statistical Mechanics, wrote this nice sentence that is very inspiring to me, saying that to understand and like thermodynamics, we need to see it not as an example of the n-body equations of motion, but as an example of the logic of scientific inference. And if you know a little bit about Jaynes, then you should know that when he speaks about the logic of scientific inference, he means probability theory, in particular, Bayes-Laplace Rule, because for Jaynes, the whole logical thinking is encoded in Bayes-Laplace Rule as a kind of even a generalization of Aristotelian logic that allows not only syllogism, but even probabilistic thinking. So then the first idea here that I had with Valerio Scarani, this is a second paper that I wrote together with Valerio Scarani in Singapore. The first idea is that perhaps we could see the reverse process as Bayesian retrodiction. Let's see where this leads us. So the construction of the reverse process. So the starting point is a stochastic transition rule. So we try to keep things as simple as possible, right? So a simple stochastic transition rule that tells you how a system with a finite number of states, X, transitions to another state, Y. And then we say that a steady state is an invariant distribution for this transition rule phi is this sigma. So sigma does not change, is a steady state. Now the idea is that you should define the reverse transition by Bayesian inversion at the steady state. So Bayesian inversion works for any prior that you plug into your stochastic transition rule. But here we are claiming that you should construct your reverse transition by doing inversion at the steady state. In this way, you find this nice property that the ratio between the forward transition and the backward transition is given by just a ratio between the values of the invariant distribution. So now you have a forward transition rule, a backward transition rule, and now we put the priors. We imagine two games basically played by two different players, a predictor whose prior is the usual prior that we consider that is plugged into the forward process, but also we put here a retrodictor that instead will have a prior on final conditions and will use Bayesian retrodiction to retrodict the initial conditions of the system. So we have two processes. We have a forward process, which is the prediction process, which is constructed by taking the forward and usual stochastic transition rule and plugging here the predictor's prior, Px, and the reverse process that is obtained from the reverse transition rule, stochastic rule, multiplied by the retrodictor's prior Qy. So just to give you a little bit more intuition about what's going on. So we have a forward stochastic process phi, a backward stochastic matrix phi hat. And if we are at steady state, by definition, prediction and retrodiction are the same. But if we change the priors of the retrodictor and the predictor, the two things will differ. So we have an asymmetry. And the idea is that fluctuation relations can be seen as measures of the statistical divergence between the predictive process and the retrodictive process. So notice that here there is still no physics. We are working only with Bayesian inference. But still already at that level, there is an asymmetry between prediction and retrodiction. So then let's measure that asymmetry by using some statistical divergence, for example, an F divergence, so-called F divergence, which are generalizations of the usual relative entropy. If for F as the function F, you take the logarithm, you have pullback-Leibler divergence, which is the usual relative entropy. But if you take a power law, for example, this becomes like a Hellinger-Renyi divergence. So then we consider this object here as a kind of fluctuating variable, which is averaged over the forward process. So then we can introduce the probability density function for this fluctuating variable in this way. It's a kind of cheating, right? Because this probability density function, we have peaks corresponding to these discrete values here, but nonetheless, by writing things in this way, we can consider a continuous variable u. Right, and now just from the definition of F statistical divergence, by having some conditions of some regularity conditions on the function F that you use for your function, which is satisfied, for example, by the relative entropy or the Renyi divergence, you can define this function G. Don't think too much. It's just a function that is uniquely defined. It's a kind of dual function corresponding to F. But anyway, the point is that for any such F divergence, you have a corresponding F fluctuation theorem that expresses the asymmetry between prediction and retrodiction. In particular, for F equal to the logarithm, we have a relation that is reminiscent of Crookes' fluctuation theorem. Okay? So now, from now on, I would like to give you some examples about how to use this formalism. So until now, we just use statistical inference and the rules of consistent logical thinking, which is to say Bayes' rule. Now we can put physics on top of it, right? So we basically change the order. People typically start from the Hamiltonian and they construct a time reverse process starting from the Hamiltonian. Here we propose a more abstract approach and introducing the reverse process as retrodiction, and then we put physics in it. For example, consider the example of a driven Hamiltonian evolution. So you have a driving protocol that goes from time 0 to time tau, and the Hamiltonian is driven by some external control from h0 to h tau. And then you have final Hamiltonian, initial Hamiltonian. So epsilon x are the energy level of the initial Hamiltonian, eta y are the energy level of the final Hamiltonian. And in this case, you have a deterministic evolution. It's Hamiltonian evolution, right? And so it means that your transition matrix, your stochastic process is actually a deterministic process. It's a delta function between y and the y that you reach from x through the trajectory. So this tells you that an invariant distribution for these things is just a uniform prior. You can think like in quantum mechanics, this would be a unitary process, and an invariant distribution for a unitary process is the uniform state, the maximally mixed state. So this leads you to conclude a relation between the two transition matrices. Now, starting from thermal equilibrium, imagining that both predictors prior and retrodictors prior are both at thermal equilibrium, you can derive the following thing. So here you have the fluctuating variable, which is the logarithm of the ratio between these two things, which can be written in this way. Now, because sigma y and sigma x are the same, they cancel out, and you're left with px divided by qy. And due to the form of px and qy, you have that this fluctuating variable is equal to beta times what? F minus initial energy plus F dash plus initial energy, which is, sorry, this is a minus F dash, sorry. So what it is, because this is closed, so the energy change of the system can be seen as work because there is no heat exchange. This is exactly the thing that we've got before, right? This is exactly Crookes fluctuation theorem. So for Crookes fluctuation theorem, you can work out in terms of retrodiction instead of a physical time reversal process. Another interesting consequence is the consideration of non-equilibrium steady states. So now you have a stochastic process with a non-thermal steady state. So some sigma that is not a thermal distribution, a Gibbs distribution. But still you start from thermal priors for predictor and retrodictor. So what is this fluctuating variable now? Again, you plug the formula of retrodiction and prediction, and you're left with this, beta times energy difference plus this. So now these things were there already in the literature and were called non-equilibrium potential, right? But typically, these things were introduced ad hoc in order to reconstruct the Jarzynski equality. Because if you don't introduce this difference of a non-equilibrium potential, you have something that looks like the Jarzynski equality, but does not sum up to 1, but it sums up to the efficacy that we have seen before. So everything, is connected here. So the point is that whereas before these non-equilibrium potentials were introduced ad hoc to have formulas working, to work out fluctuation relations, here these non-equilibrium potentials are just understood as remnants of Bayesian inversion. So to me, this has a very nice explanatory power. We don't need to rely on some ad hoc construction, but everything works just because Bayes-Laplace Rule. But also things working for quantum processes. The interesting thing is that there were claims in the literature such that fluctuation relations and fluctuation theorem would hold for quantum processes only in the case of a closed process, or at least unital process, not for general quantum processes. And that would be strange, right? Because quantum processes just generalize classical stochastic processes. So one would expect that they would satisfy all the relations satisfied by classical processes and more, not less. And indeed, the problem is that people in that literature were defining a reverse process by using a wrong rule, by using by not using Bayes-Laplace rule, but by constructing the process in a wrong way. Because if you assume that your stochastic matrix actually has some kind of quantum explanation inside in terms of some preparation rho x, some CPTP map E, and some measurement pi y, which can be a P of M, for example. Then you just apply the formalism of quantum retrodiction, which is to say, basically, the thing that you should see is this construction of the reverse map, which is the PETS reverse map, by the way. So just by using the formalism of quantum retrodiction, everything carries through directly, and you have the Bayesian inversion of your channel. So what you would do with Bayes-Laplace rule is just done by means of quantum retrodiction. So our recipe basically agrees with the formalism of quantum retrodiction that was already there. So we are bringing things inside to make the picture easier to understand. And this leads me to the conclusions. So a summary. what I would like you to take home as a message, and what I would like you to think about, and maybe to see whether you're convinced or not by these arguments. So first of all, I would like you to understand that the role of retrodiction, that retrodiction, in particular Jeffrey conditioning, plays a role in thermodynamics and statistical mechanics. And then another possibility is that from what I showed you, one might understand the reverse process not as a physical time reversal, not as something that you do at the level of Hamiltonians, but something that you do at the level of logical inference as retrodiction. In the same way, fluctuation relations are quantitative measures of the asymmetry between prediction and retrodiction. And again, fluctuation relations seen not as consequences of complex microscopic balancing mechanisms, called, for example, microscopic reversibility or detailed balance, but coming from logical consistent inference, which is to say, like, what would a rational agent say in the face of the uncertain evidence that he has about the system. And then a final thing that it's a little bit more suggestive, it's a little bit of a stretch, but I would like to think of the logical origin of the perceived one-wayness of time. That is to say that this unbalance between forward process and reverse process is something that comes to us because of the asymmetry between prediction and retrodiction. Think of a gas that starts, for example, all in the corner of the room, and then you let it expand. It is much easier to predict that the gas will expand than to retrodict where the gas was coming from once you have the gas expanded already in the room. Okay, and that brings me to the end of the talk, and I thank you for your attention.
Thank you very much for this perfect timing. You aim for 35 minutes, you had 35 minutes. Excellent. Any questions from the audience? Okay, I don't see any hands. So maybe let me start with some naive questions.
Yes.
So doesn't the word retrodiction itself imply some kind of before and after relations?
Yes, but if you flip the arrow of time, so imagine that you really flip the arrow of time, right?
Yeah.
Then the predictor would become a retrodictor and vice versa. But still you would observe the same kind of asymmetry. Like, however time is oriented, retrodicting is always harder than predicting somehow. So retrodiction happens later, but at a kind of it's later, but logically later, rather than temporally later. Then, of course, typically we experience some time behind us. No, things work because there is this parameter t then keeps growing. But if instead of growing, it would keep decreasing, right? I would say that we wouldn't see any change in the laws of thermodynamics. We would still have a second law. We would not see things becoming more ordered, because prediction would, I mean, it's easy to get around here, but if we were starting from the future, then we would have as prior the state of the system at the future time, and prediction would be what we call before retrodiction. So I understand. It seems that I'm just going around in circle, but what I would like to say is that maybe what the second law is telling us is not something about the arrow of physical time, but it is more about the arrow of a logical time. It tells us that there is asymmetry between prediction and retrodiction. I would like to think like that, but this is just an indication, right? It's not a proof for this, of course. I wouldn't even be sure that you can prove any such statement.
So maybe differently, I guess maybe you were suggesting something like the following. If we take for granted the asymmetry between predictions and retrodictions, then it might actually suggest a natural arrow of time, so to speak.
Yes, but in a way, you don't have to take for granted that there is an asymmetry.
Okay.
The asymmetry comes out just because of the Bayes-Laplace rule, which is basically, which in turns is the only way that a rational agent should reason, right? So because of Bayes-Laplace rule that can be derived in many ways from just axioms, from an axiomatic approach, just from Bayes-Laplace rule already there, you have an asymmetry between prediction and retrodiction. However, the time flows.
But that asymmetry has to be rooted in the asymmetry in the priors. I mean, if this.
Yes, exactly. So everything is. I mean, one can say that, you know, for predicting, you have the prior at hand, right?
Okay.
So in that sense, it's asymmetric. It's not symmetric.
Right. So any other questions from the audience? Yep. Yes. No. Maybe. Okay. I don't see any hands. Maybe it's too early here.
Okay.
So I guess in this case, let's thank Francesco again. I think I'll have to catch up with you again to talk more about this. So see you sometime in the future.
Okay. Thank you. Thank you for the opportunity. Bye.
All right. Yes.